Hey everyone, I hope you're doing well today. In this video, I'm going to be talking about complex numbers, how to plot them, and represent them in different ways. Let's go over the different forms of complex numbers. The first form we'll talk about here is called standard form, and just be aware that besides standard form, we can also call this rectangular form. So just two different names for the same thing. In this form, complex numbers are just represented in the form of z is equal to a plus bi. This a here represents the real part of the complex number, and this bi over here represents the imaginary part of the complex number. Let's look at an example real quick. We have z is equal to negative 2 minus 2 root 3i. To plot this complex number, we start by drawing a horizontal axis, and we can call this the real axis. I'm going to label that with a capital R. And then we're going to draw a vertical axis. Now, instead of a real axis over here, this is actually going to be our imaginary axis. I'm going to use a lowercase I to represent that. Put a couple tick marks here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay. So this form really isn't too bad. If you take this negative 2, which is the real part, you just start at the origin and you move 2 units towards the left. Okay? And for this negative 2 root 3, if you plug that into a calculator, that's roughly negative 3.46. That just means we're going to be moving 3.46 units down here. So right around here sounds good. So again, just to simplify this a bit, when we're in this rectangular standard form, we're just moving negative 2 units or 2 units to the left, and then 2 root 3 or negative 2 root 3 units down, which is roughly negative 3.5. At this point, you can just put a point here, and we're going to call that our complex number, or z. And that's the visual representation of using standard or regular form of complex numbers. Really, you have this real part and you just move left and right along the real number line, and then you move up and down along the imaginary axis, and then you can plot your point or you can plot your complex number. Besides representing complex numbers using standard or rectangular form, we have a second form here called the polar or the trig form or the trigonometric form. Okay. Now, for this one, we can just represent our complex numbers using a different way, and we can say z is equal to r times cosine of theta plus r times sine of theta times I. And while you might see it in this form sometimes, just notice how both of these terms actually have a common factor of r. So more commonly, you'll see this written as z is equal to r, the common factor, multiplied by the quantity of cosine of theta plus I sine of theta. Okay, both of these mean the same thing. You can just see here that the radius here, or r, I'll label that right over here. This is the radius. Since it's a common factor, we can factor it out in front. And just keep in mind that the radius is really just the absolute value of the complex number, or how far it is from the origin. Now let's look at that same complex number that we had on the left side, but let's look at it in this new form. So instead of writing z is equal to negative 2 minus 2 root 3i, I'm going to write over here z is equal to 4, which is our radius, times the quantity, and I'm going to write cosine. I'm going to give you an angle measure here in radians, which is 4 pi over 3, plus I times sine of that same angle measure of 4 pi over 3. So it turns out we can write our complex number that was in rectangular form into this new form, which we call polar or trigonometric form. The two key pieces of information that I want to point out right away is that this 4 represents our r, or our radius, and this 4 pi over 3 is telling us our angle measure in radians. Let's see how plotting this complex number would look like from this form. So here we have our real number line, so I'll put that as an r, and we have our imaginary one, so I'm going to put that up and down right over here, and that's going to be, I'll put a little I for imaginary again, and let's just go with maybe 1, 2, 3, 4, 5 again. 3, 4, 5, 1, 2, 3, 4, 5. I don't really need these up here because it's not going to be up here, but that's okay. So let's talk about this angle of 4 pi over 3. We know right over here that's pi, that's 180 degrees. So 4 pi over 3 is an extra 1/3 of a pi, and that's going to be like 60 degrees or like right around here. So here you can see that this is our 4 pi over 3. But we actually don't know like where to actually plot the complex number along this line, right? Like it could be anywhere along here because we have the angle measure correct, and that's where the radius comes into play. So we know our radius is 4, so starting from the origin here, we just move 4 units, and once we get to 4 units, we can actually plot our complex number, and that will be right over here. And going back to our other diagram for rectangular form, that actually holds true over here as well, which should make sense that the radius here, or the absolute value, would be 4. And you can check this using the Pythagorean theorem, but I promise you this works out. So big picture, what do you want to take away from these two forms is that when you're dealing with the standard or rectangular form, to plot them, we're really just saying like, how far left and right and then how far up and down, kind of like what you traditionally do to plot points. And when plotting the same complex numbers here, you just want to make sure you're understanding that the angle measure is just how far around you're moving, and then the radius is telling us like how far out to go. So one is talking about left, right, up and down, and one's talking about moving in a circular motion and then when to stop based on like where you are along the circle. I hope that you now kind of see the connections between these two different forms and how they're both just representing the same thing in a slightly different way. Now I'm going to go over some practice problems where we convert from one form to the other. So in that introduction, I talked about an example where we had z is equal to -2 minus 2 root 3i. And while that was in rectangular form, I also mentioned that we could write it in a polar form. And that polar, or that trig form, is represented by 4 times the quantity of cosine of 4 pi over 3 plus this I times sine of 4 pi over 3. In this first example, I'm just going to try to show you why these two forms are really the same thing. So I'm going to start off by distributing this 4 here to both parts inside. And so we can rewrite this trig or polar form as z is equal to 4 times cosine of 4 pi over 3 plus this 4i times sine of 4 pi over 3. Okay, so basically the same thing, just distributing the radius out. Now it's important to remember that rectangular form is really z is equal to a plus bi. So let's just hold on to that for a second here. And this -2 is the a, and the -2 root 3 is the b. So rewriting this polar or trig form, we can write this as 4 times cosine of 4 pi over 3, and add that to 4 sine 4 pi over 3i. If that's the case, we should be allowed to say that this over here really is going to be representing our a value, or the real part, and this 4 times sine of 4 pi over 3 is really representing that b value. I'll write that right over here. Given that, we can say that a is equal to 4 times cosine of 4 pi over 3. I'm just going to put that in parentheses. And b is equal to 4 times sine of 4 pi over 3. Let's see what this looks like on a plot. So here we have our horizontal axis. I'll call that the real one. And here's the vertical axis, and that'll be our imaginary one. So put it over here, and I'll put a little I to represent. Since a is -2, we know we're going to be moving 2 units to the left here. And since b is -2 root 3, we can write that right over here. Here's technically where our complex number is, and its distance from the origin, or its absolute value, we can call the letter r. In radians, we have 0 over here, we have pi over 2, and then we have pi, and then 3 pi over 2. That means this reference angle here is pi over 3. Now thinking back to your trig ratios, you remember that sine of theta is equal to y over r, cosine of theta is equal to x over r, and tangent of theta is equal to y over x. And since these ratios pertain to the unit circle where the radius is equal to 1, if r is equal to 1, then the sine of theta is really just equal to the y value, or the vertical distance, and the cosine, if we do x over 1, that's just going to be the horizontal distance, or x here. It's important to try to keep in perspective here that if we have a unit circle, that means the radius by default is going to be 1. However, since our radius is 4 here, hopefully it makes sense why we're scaling everything 4 times bigger. So if you check a unit circle and you see what sine of 4 pi over 3 is, you'll see that that's actually going to be -√3 over 2. And if you take this 4 and multiply by it, and you multiply that by 4 over 1, you're going to see where the -2√3 comes from. And as for cosine, if you were to take cosine of 4 pi over 3, that's going to be -1/2. You can check the unit circle or draw one of your special triangles. And since that's for a unit circle where the radius is 1, if you scale it up and multiply that by 4 here, since the radius is 4, you're going to notice that we actually get a value of -2. Hopefully it makes sense here that since our radius is 4, we just have a bigger version of the unit circle. So big picture here, just trying to help you understand that compared to the unit circle, we just have a bigger circle here and everything is scaled up by a factor of 4 since our radius is 4 times bigger. So let's try taking a complex number that's written in this rectangular or standard form and try to rewrite it into polar or trig form. And just keep in mind what we're doing here is we're taking that form of z is equal to a plus bi, and we're going to convert this to that form of z is equal to what was it again? It was r times the quantity of cosine of theta plus sine of theta I, or I sine of theta. Either one is fine. Just seeing what this roughly looks like here, we can take this negative 2 root 3, and that lets us know that we're going to be moving negative 2 root 3 units this way. So I'll just put that as 2 root 3, and we're moving 2 units down, so that's not as far down, but that'll be 2 units. So now that we know our complex number is down here in quadrant 3, we want to find the distance of it from the origin. And that's going to be our radius, also known as our absolute value of the complex number. So to find the value of the radius here, or the hypotenuse of this right triangle, we can say that r squared is equal to this a squared plus b squared, right? So just a little bit of Pythagorean theorem here. So even though I didn't write it earlier, this 2 root 3 is really negative 2 root 3, and we can call that our a value. That's our left and right. And our 2 here, this is really negative 2, and that's our b value. That's our vertical distance up and down. So to find r, or the distance from this to the origin, we can take the square root of both sides, and we'll find that r is equal to the square root of the a value, which is negative 2 root 3 squared, plus the b value squared, which is going to be negative 2 squared. So if we square that negative 2 root 3, 2 times 2 is 4, and root 3 times root 3 is 3. 4 times 3 is 12, so we'll have a 12 over here. And the negative 2 squared, that's just going to be positive 4. So we can write that right over here. And then we can combine the 12 plus 4 and say that the radius is going to be the square root of the 16. So we can find that the r value is going to be equal to 4. And we needed that for our new form. Now at this point, it's important to remember that a is just equal to r times cosine of theta, and b is equal to r times sine of theta. Since we know that a is equal to negative 2 root 3, we can substitute that in. We know that the radius here is 4, we can substitute that in as well, and we have times cosine of theta. And we'll find that cosine of theta is equal to negative root 3 over 2. And taking the arc cosine of both sides, we can say that theta is equal to arc cosine of negative root 3 over 2. Now to figure out what this is, you can either plug it into a calculator or look at a unit circle, but I'm just going to draw a right triangle here. I know I'm not going to use the 45-45-90 triangle, and we're going to use a 30-60-90 since we have the root 3 here. Okay, so the way it's drawn, this would be the 30 degrees and this would be the 60 degree angle. So what angle would we use cosine for to get the root 3 over 2? Well, we need adjacent over hypotenuse. So I think that this one is going to be, I think this one right here is going to be our adjacent, and this will be our hypotenuse. So I think our angle measure here is going to be 30 degrees. Now just be careful and don't actually use that 30 degrees, right? So we're supposed to be in quadrant 3, so 30 degrees is just kind of our reference angle. So we need to see, like, what is 30 degrees past 180 degrees? And 30 degrees past it is going to be 180 plus 30, so that's going to be 210 degrees. And that does put us in quadrant 3 and has this triangle. It also makes sense why we have a negative value for this negative root 3 over 2. Since if you think about like ASTC, we should have a negative value in quadrant 3 when we're taking cosine. Okay, if we convert this degrees into radians, I believe this should be, what, 7 pi over 6? Because pi over 6 is 30 degrees, so yeah, it's just another sixth on top of it. Okay, so at this point, we found out that our theta here is 7 pi over 6. For this other equation we know b is negative 2. We found r is 4, and that's times sine of theta. Then we can divide both sides by 4, just like we kind of did earlier. And we can say that sine of theta is equal to negative 1/2. Taking arc sine of both sides, we can say that theta is equal to arc sine of this negative 1/2. And basically using that same triangle we did earlier here, since they should be the same, this is 30, this is 60, this is 1, 2, and root 3. We should be using this 30 degree angle again, since this is going to be our opposite side and this is going to be our hypotenuse. So it's still going to be of this 30 degrees. So this should match, right? So this is still going to mean that our theta here is going to be 7 pi over 6. It should match exactly what we had earlier. Now let's say you want to be super big brain here. So remember that sine is equal to y over r, and then cosine is x over r, and tangent of theta is equal to y over x. So remember, y is represented by kind of our b value, right, our up and down, and our x value is represented by our a value, or left and right. Hopefully you remember your trig identity. We can say that tan of theta is equal to sine of theta over cosine of theta. So what we can actually do here is just simplify this whole thing down to just saying this is going to be b over a. Okay, so when we say that this tangent of theta is really just equal to b over a, we can substitute in our b value and say that's -2. And if we plug in our a value here, that's going to be -2 root 3. Simplifying this a bit, this -2 over -2 just becomes 1. So we can just write here 1 over root 3. Rationalizing this denominator and multiplying this by root 3 over root 3, we're going to get root 3 over 3, and that's what tangent of theta is equal to. To find theta, you can just take arctangent of root 3 over 3. And if you do that, I promise you, you're also going to get this angle measure of 7 pi over 6. Now that I've showed you 3 different ways to find this theta, or this angle measure of 7 pi over 6, let's use that angle measure as well as the radius we found earlier to write our polar or trig form, and write z is equal to 4, that's the radius, times the quantity of cosine of 7 pi over 6, plus we can write I times sine of 7 pi over 6. Remember, you can put the I in the front or in the back, either one is fine, but this would be our new form. Let's try another one here. Let's say we have the square root of 21 plus I root 7. Our a value, or our left and right, is going to be the square root of 21, and our b value here is going to be the square root of 7. Making a quick sketch here, we can take a look what this looks like. Let's say root 21 is going to be going in this direction. Put that right over here. And root 7 is a smaller number than root 21, so I'll put that right over here and don't go up as much. And while we have rectangular form, we're trying to go to polar or trig form, so we'll need the radius here, or the absolute value of this complex number. To find the radius of the circle, that's just going to be the square root of the a squared plus b squared. So that's going to be, what is this root 21 squared. And we're also going to have to add on here the root 7 squared. So write that root 7 squared right in there. And root 21 squared, that's just going to be a normal 21. And the 7 squared is just going to be a normal 7. So 21 plus 7, maybe we can just simplify that down to writing 28. Okay, simplifying that just a little bit more, we can pull out a perfect square and say this is going to be 2 root 7. So that's our radius, or the absolute value of this complex number. Now that we have the radius, let's work on finding the angle measure. Now in the last example, I talked about how a was equal to r times cosine of theta, and I also showed how to find the angle measure when we knew that b was equal to r times sine of theta. But instead of writing all that extra work, try to remember that third method I mentioned where we have actually the b over a, right? So we really have the sine over cosine using that trig identity. Substituting in those values we know, we can say tangent of theta is going to be equal to b over a, and in this case it's going to be root 7 over root 21. And using your radical properties, you can really say that this is just the square root of 7 over 21, but that's just 1/3, right? And if you want to separate the radicals again, that's perfectly fine. The square root of 1 on top is just 1, and the square root of 3 on bottom is just going to be root 3. And rationalizing this, we can multiply the top and bottom by root 3, and say that tangent of theta is equal to root 3 over 3. Now if that's true, we can take the arctangent of both sides and say that theta, or our angle measure, is equal to the arctangent of this root 3 over 3. Now if we sketch one of those triangles again, and we're going to use that 30, 60, 90, just because we have a root 3 again. Here's our 1, 2, and root 3. So remember, tangent is opposite over adjacent, so if this is our angle measure, this would be the opposite and this would be the adjacent, and we would get this 1 over root 3, which we know is the same thing as root 3 over 3, right? Just kind of rationalizing that denominator. So it looks like 30 degrees is going to be our angle measure here. We can say that theta is equal to 30 degrees, or in radians instead, we can say this is equal to pi over 6. And since we knew from the rectangular form that we're in quadrant 1, we don't have to do anything with the signs here. It's positive, it's all good. We have your A, S, T, C. Everything was supposed to be in quadrant 1 from the start, so don't worry about any extra reference angles or going into other quadrants. So we found our radius earlier, and we just did some work to find our angle measure of pi over 6, or 30 degrees. So I think we're ready now to write this in our trig or polar form and say z is equal to the radius, which is what, 2 root 7 we found, and that's going to be multiplied by cosine of pi over 6. That's the angle measure we just found, and add that to I times sine of the same angle measure, pi over 6. And there we have it. We converted the rectangular form into this polar/trig form. Now that we've talked about going from rectangular to polar or trig form, let's go the opposite way. Let's start with the trig form here. We have z is equal to the square root of 8 times cosine of negative pi over 3 plus I times sine of negative pi over 3. Let's take this polar or trig form and turn it into that rectangular form, which is z is equal to a plus bi. Let's first establish that our r, or our radius here, is the square root of 8. And our theta, or angle measure here, is going to be negative pi over 3. And if it helps you visualize this a little better, you can just remember that this is negative 60 degrees, also known as 300 degrees, right? So it's going to be in quadrant 4. Now let's take this cosine of negative pi over 3, and let's find the value of it, okay? So we'll take that right over here and see what the value of cosine of negative pi over 3 is. Now just to double check where this is, this negative pi over 3 is going to be down here in quadrant 4, and right about here maybe, right? So that's going to be negative pi over 3. And if it helps you to think about this in degrees, this is negative 60. So there's our theta, and let's see if we can find cosine of it. Given that this is a 30, 60, 90 triangle, our hypotenuse is going to be 2 here, our adjacent side is going to be 1, and our opposite side here is going to be root 3. Taking cosine of this angle, that's going to be adjacent over hypotenuse. So we can say that cosine of this negative pi over 3 is going to equal 1/2. And if you just want to double check your signs, remember your ASTC. Cosine is going to be positive in quadrant 4, so we are good with this positive 1/2. Now let's see if we can figure out what this sine of negative pi over 3 is. Well, it's the same sketch. I'm just going to redraw it so it's a little bit easier to see. We have this angle right down over here. Here's our angle measure again, and we have our root 3, 1, and 2. And sine of this angle measure is going to be opposite over hypotenuse. So we can say that sine of this negative pi over 3 is going to be equal to negative root 3 over 2. Just keep in mind, since cosine is the only function that's positive in quadrant 4, that when we're taking sine of this angle measure, we should get a negative value. So make sure you have a negative here. Now that we know what cosine of negative pi over 3 is and sine of negative pi over 3, let's substitute those values back in. So we have z is equal to the square root of 8 multiplied by our newfound value of 1/2 here plus I times negative root 3 over 2. Before we go any further, distribute the square root of 8. I'm just going to rewrite this as 2 root 2. If we just simplify that radical. So cleaning this up a bit, I'm going to say z is equal to 2 root 2 times a quantity of 1/2 minus, and I'm just going to turn this around a little bit and write root 3 over 2i. Distributing this 2 root 2, we'll get 2 root 2 over 2. And distributing it over here, we'll get minus 2 root 6 over 2i. This left fraction can simplify by canceling out these 2's. And we can finally write a rectangular form here of z is equal to root 2 minus root 6i. And there you have the rectangular form for the complex number. And here's one last example where we'll take another trig or polar form and convert it into rectangular or standard form, whatever you want to call it. So we have 2 times this cosine of 4 pi over 3 plus I times sine of the same 4 pi over 3. To turn this into that form of z is equal to a plus bi, we're going to have to first find what this cosine of 4 pi over 3 is, then find what the sine of 4 pi over 3 is. Now let's go ahead and do those at the same time. So we can just make a quick sketch here. Since 4 pi over 3 is over here in quadrant 3, we can draw a triangle here and then label our theta. 4 pi over 3 is equal to 240 degrees, so right over here is 180. Given that this is a 30, 60, 90 triangle, our measurement of 1 would be here, 2 is here, and root 3 is right over here. Taking cosine of this angle measure, the adjacent would be 1 and the hypotenuse would be 2. And because cosine is negative in quadrant 3, we can say that cosine of this 4 pi over 3 is going to be equal to negative 1/2. As for sine of this angle measure, that's going to be opposite over hypotenuse. We can write sine of 4 pi over 3 is equal to root 3 over 2. And since sine is also negative in quadrant 3, let's put a negative on there. Substituting in our newfound values of negative 1/2 and negative root 3 over 2, we can say that our complex number, z, is equal to the radius, which is 2, multiplied by negative 1/2 minus root 3 over 2i. Distributing this 2, we can say that 2 times negative 1/2 is going to be negative 1. And distributing this 2 to this negative root 3 over 2, that's just going to be negative root 3. And there we have our complex number written in rectangular form now. And that wraps up this video on representing complex numbers in polar form as well as rectangular form. I hope you found this video helpful and keep up the good work.